Hi everyone! So in this video, we're going to start talking about one of the most important topics in Calculus 2, which is approximating areas. So I want to start by just talking about, what does the word area even really mean? So area refers to a measurement of space, right? But specifically, it's two-dimensional space. So the way I'm going to say it here is that area is a measurement of the space in a two-dimensional region. And the word space is a little bit funny to use here because usually space actually refers to a three-dimensional shape, but I think you all know what I mean. So the word volume, right, that's what we use when we're talking about a three-dimensional. Like if you have a sphere or a cone or a three-dimensional shape, then we talk about the volume. When we're talking about area, we mean a flat shape. So something like a rectangle or a triangle or a circle, those are shapes where we can find the area. So just to give a couple of quick examples, let's say that you have a rectangle. So a rectangle, looks something like this. So if you have a rectangle and you're trying to find the area of a rectangle is going to be equal to the base times the height. So area of a rectangle is base times height. And another simple example would be a triangle, right? So if you have a triangle, how do you find the area of a triangle? Well, you have to measure the height from the top down to the base, a perpendicular height like that, and that is h. And then the area is going to be 1/2 times the base times the height. And just to throw in one more example, you could also look at the area of a circle. Let me just scooch this down. That's what we'll be looking at next. So a circle, how do you find the area of a circle? Well, then you have to measure the radius of the circle, right? So the radius is the distance from the center out to any point on the circle, and the area is equal to pi r squared. So these are basically shapes that you should know how to find the area from, from like a geometry class, right? So what we're going to be focusing on, at least to start with in Calc 2, is finding the area of a region bounded by graphs. So let me write that down and then we'll jump into a couple of examples. So in Calculus 2, we will be focusing on finding the area or areas of regions bounded by graphs. So we'll see that that's something that is basically going to be coming up kind of all throughout the quarter. And today is just sort of our first taste of it. So one example that we could do without knowing any of the kind of tools that we're going to eventually have in Calc 2 would be, let's say that you have a line. So you have the line, let's say f of x is equal to 3, right? That's a horizontal line at a height of 3. So if we wanted to find the region bounded by that line, and then also by the line, vertical line, x is equal to 4, and the vertical line, x is equal to 0. So basically, and then the x-axis, so this area here. So if we wanted to find the area of the region bounded by the function f of x is equal to 3, the x-axis, y is equal to 0, or sorry, x is equal to 0, that would be horizontal, or sorry, vertical line, and x is equal to 4. So that would be the region that we just highlighted in blue, right? So how would you find the area of this region? Well, in this case, it's just a rectangle, right? So we know how to find that area. So the area is going to be equal to the base times the height, which in this case is going to be 4 times 3, which is equal to 12. So I'm basically just kind of restating a simple geometry problem, but kind of in the words of graphs, right? So instead of just saying find the area of this rectangle, we're kind of thinking of this rectangle as being a region bounded by different functions and different vertical and horizontal lines. So we could also do something similar with another type of function. So in this graph, we have the function f of x is equal to, or let's call it g of x, is equal to negative x plus 5. So let's say now we wanted to find the region bounded by g of x is equal to negative x plus 5, and the x-axis, I guess I should have said here the word and. Let me just fix that to make this sentence a little smoother. And let's say we're going from x is equal to 0 to x is equal to 5. So what region are we talking about? In this case, we're talking about here. So the region kind of closed off between x is equal to 0, that would be here, x is equal to 5 would be here, and then the x-axis, and then our graph negative x plus 5. So what would be the area in this case? Well, this is a triangle, so we can do 1/2 times base times height, which in this case is 1/2 times 5 times 5. And so our area in this case would be 25 over 2. So the examples we've done so far both were triangles and rectangles, right? So there were shapes that you already kind of can just use geometry to find the area of. For the most part, though, in this class, we're going to be working with functions that don't have quite as nice a shape. So let's say instead that we wanted to find the area of the region bounded by, so this function here is now f of x is equal to x squared. And we're also going to be bounding it by the x-axis. And we're going to be looking in between x is equal to 0 and x is equal to 3. So what region are we focusing on in this case? Well, we're starting at x is equal to 0, we're going up to x is equal to 3, and then we're going between the x-axis and this graph. So we're looking at this area here. So what's different about this shape? Well, you might look at it and say, well, it kind of looks like a triangle, but it's not, right? It's curved. So basically, we don't yet have the tools to find the area of a curved shape like this. You know, we can't use the circle formula, we can't use the rectangle formula, we can't use the triangle formula. None of those really fit. So let me kind of write that down. So we don't, and I'll say yet because starting like next week, we'll see how to actually find this area. But we don't yet have a way to find, the exact area. But we'll see is that we can approximate the area. And what are we going to use to approximate the area? We're going to use rectangles. And so we'll see on the next page what that looks like. But basically what we're going to do is we're going to take this green region that I shaded in here, and we're going to kind of break it down into little rectangles. So it's not going to give us the exact region. It's going to have kind of a jagged edge to it instead of this smooth edge with the parabola. But but we'll see that depending on our choice of how many rectangles we use, we can actually get really close to finding the actual area. And by the way, so if you remember back to Calculus 1, you'll remember that at the very beginning of the quarter, we were talking about tangent lines, and we were doing this thing where we were approximating. We were trying to figure out what is the slope of the tangent line. And the way we did it is that we used secant lines, right? And we kind of found all these different slopes and sort of tried to see what the general trend was. And we're going to basically be doing something really similar for finding areas. So we're going to see that we're doing this method of approximation. And then just like in Calc 1, so remember in Calc 1, we started off doing all these approximations, we did limits, and then eventually it was like, oh, actually we can just take the derivative and we can use these rules. And so it's going to be really similar in this class. We're going to start by doing all these approximations and kind of doing things the hard way in a sense, but then eventually next week we'll find out that there's actually simpler, more straightforward ways to answer a lot of the questions that we're working on in this video. And so with that in mind, you'll see that the stuff we're talking about today is you're probably going to be like, how is this at all related to what we talked about yesterday with antiderivatives? And, you know, it's not going to be clear yet how they're related, but we will see that they are related. Okay, so how do we actually go about using rectangles to approximate area? So let me just write a title up here. So using okay. And by the way, the kind of fancy name for what we're about to do is that they're called Riemann sums. Okay, so what we're going to do, I mean, there's a lot of ways that you could imagine doing this, right? Like, so again, we're focusing on the region between 0 and 3, so this curved region here. And there's a lot of different ways you could fill this region up with rectangles. But we want to kind of take advantage of the knowledge that we do have. And I guess what I mean by that is you don't want to just, so like if you were to kind of just draw some random rectangles in, you know, willy-nilly, you wouldn't really have a good way of figuring out what the heights were of those rectangles. And we need to be able to figure out the areas of the rectangles. So when we draw these rectangles, we're always going to be using points on the graph to give us the heights. So we'll do this a few different ways. The first way we're going to do it is so we have this, we're going from 0 to 3, right? So that's the kind of the x-axis part that we're looking at. We're going to break it into 3 pieces. So we're going to draw 3 rectangles. And so what we're going to do is each of these intervals, so we have the interval from 0 to 1, from 1 to 2, and from 2 to 3, each of those is going to form the base of a rectangle. And what we're going to do in this example is we're going to always go to the right side of each interval and use that to find the height. So what I mean by that is that if we look at the rectangle that's going to be between 0 and 1, we're going to go to this point at 1, and this point here is what's going to determine the height of our rectangle. So we're going to go down and across and just draw a rectangle that has the right endpoint determining its height. And so then for the second interval, so from 1 to 2, again, we're going to go to the right side of that interval and we're going to go straight up and find the point that lies on the graph at an x value of 2. And then now that we know that that's the height of the rectangle, we can go straight across and straight down and draw a rectangle. So here is our second rectangle. And then our third rectangle, we're going from 2 to 3, and we're going to draw a rectangle where the height comes from the right side, so it comes from this 3. So we go to a height of 3 squared, because our function is f of x is x squared, and we draw a rectangle. Okay, so this, if we add up the areas of these 3 rectangles, it's going to give us an approximation for this area that we have shaded in green on the previous page. Now you'll look at it and you'll say, okay, that's not going to be very close, and we'll see basically how to do a better job in a few minutes. But you can at least see that it's not super far off, right? We're somehow kind of mimicking the shape of this graph because we're using these points that actually lie on the graph to determine our heights. Okay, so how do we find the area here. So I'm going to use the letter A to represent the actual area. And so that's why I'm going to say A is approximately equal to, because the area we're going to write down here is not the actual area under the graph. So maybe let me even, I'll highlight the actual area in green so we can kind of contrast them. So here's the actual area. Okay, so the area is approximately equal to, so what we're going to do is we're just going to do base times height for each of these three rectangles. So in this case, the base of each of them is just 1. So we can say base, I'm still going to write down even though it's 1, so base times height. So what's the height of the first rectangle? The height of the first rectangle is 1. What's the height of the second rectangle? It's 4, right? So we have 1 times 4. And then what's the height of the third rectangle? It's 9. So we have 1 times 9. So each of these is coming from base times height, base times height, base times height. And by the way, so in this case, we have like a nice graph and we can easily see what the heights are, but how would you figure out these heights if maybe you had a function where it wasn't so easy, it wasn't like an integer value? Really all we're doing is we're plugging the endpoints into the function, right? So this function is f of x is equal to x squared. So where is this 1 coming from? This 1 is f of 1. And this 4 is f of 2. And this 9 is f of 3. And the reason that we're plugging in 1, 2, and 3 is because those are the right endpoints of our intervals. So we'll see in a minute, we'll do what's called a left-hand sum and use left endpoints. And in that case, we'll actually be plugging in 0, 1, and 2 to get our heights. So you're always plugging in whatever kind of end of the interval you're using. Okay, so what does this give us? If we add this all up, and I guess I'll continue to use this approximate. So we have 1 plus 4 plus 9, so that is 14. So that is our approximation of what the actual area is. And as you can see from this picture, it's an overestimate, right? The purple rectangles are bigger than the actual region that we're doing. So in a minute, we'll get into how to make this approximation better, but before we do that, I want to show you how to use a different type of sum that's called a left-hand sum. So this type of sum that we did right here, this is called a right-hand sum, and let me write that down. So this is called a right-hand sum because we used the right endpoint of each interval to find the height of the rectangle. And by the way, there's kind of a shorthand for referring to this type of sum. And the way we can refer to it is we can say it's R3. So R3 is equal to 14. So R3 means basically a right-hand sum. And this 3 refers to the fact that we had 3 rectangles, because what we'll see in a minute is if we make more rectangles, we actually get a better approximation. But so if you want kind of a shorthand to, and I'll be using this, I don't know if it will come up on the homework so much, but definitely on the worksheet that goes with this video, you'll see this language come up. So in a minute, we'll do a left-hand sum, and that would be L3. And then there's also such thing as a midpoint sum, and that would be M3. So the R here refers to the fact that it's a right-hand sum. The 3 refers to how many rectangles we're using. Okay, so now let's do a left-hand sum. So basically, we're going to do a very similar process. The only difference is, and let me maybe actually shade in again the actual region that we're looking for. So the only difference is now when we divvy this region up into 3 intervals, we're going to be using the left side of each interval. So what that means is that for the first interval, the height is actually going to be 0. So there's not going to be an actual rectangle here. And that happens sometimes, especially with left-hand sums, it tends to happen because if your function goes through 0, 0, that means that the left endpoint is just going to have a height of 0. Then our second interval from 1 to 2, well, we go to the left side of that interval, so that's 1, and we use that point to determine the height. So that gives us a rectangle with a height of 1. And then for our next interval from 2 to 3, we go to the left side of that interval, so that's 2, and we go up to the graph, and that gives us a height of 4. And so this is our 3 rectangles. And so again, you can look at this and say, okay, that doesn't look like a very good estimate. It's really so the last one was an overestimate, right? It was like way too big. This one is way too small. And again, we'll see how to get a better estimate in a moment, but I just first wanted to introduce you to the difference between the right and left-hand sums. So in this case, what we can say is that the area is approximately equal to, so the base of each of these rectangles is still 1, right? So we have 1 times 0. That's the base times height for the first rectangle. Then we have 1 times 1. And then we have 1 times 4. So again, where are that 0, 1, and 4 coming from? That is f of 0, f of 1, and f of 2. And the reason we're plugging in 0, 1, and 2 is that those are the numbers on the left side of each of these 3 intervals. And so we find that the area is approximately equal to, so we have 0 plus 1 plus 4, so that's 5. So basically, from what we just found here, we can conclude that the actual area is somewhere between 14 and 5, right? Which is kind of a big range, but it gives us kind of a lower and upper bound. And so what would we refer to as, or what would we refer to this sum? This would be a left-hand sum. And so we would call this one L3, and we would say L3 is equal to 5, because when we did a left-hand sum with 3 rectangles, how did I say it here? Yeah, 3 rectangles, we got an area of 5. So I want to quickly just show you, we're not going to go through it in as much detail, but I just want to show you what it would look like to do something else called midpoints. So if we wanted to use midpoints, we would basically do the exact same thing, except for each of these 3 intervals, instead of using the left or right-hand side of the interval, we would use the point exactly in the middle. So let me just, again, shade this in, and I'm not going to actually calculate this area, but just for the sake of time, but I'll draw the picture so you can at least see like what it would look like. So if you wanted to use the midpoints, you would go to the middle of each of these intervals. So in this case, that would be like 1/2. So that would give you a height here, and that would determine the height of your first rectangle. And then you would go to 1.5 or 3/2 and go up here, and that would give you a height of your second rectangle. And then the last one, you would go to 5/2 or 2.5 and go straight up and find the height at that point. And then that would give you your third rectangle. And so if you wanted to find the area for this one, this is a good example of one where you can't just necessarily read the number off the graph. You would actually have to plug each of these numbers in. So to find the height for the first one, you would want to plug in 1/2 into your function. To find the height for the second one, you would want to plug in 3/2. And to find the height of the third one, you would want to plug in 5/2. And so this is a picture of, this is M3. So again, that's because this is a midpoint sum, and the 3 comes from the fact that we have 3 rectangles. And I don't know off the top of my head, I didn't do this one in my notes, so I don't know what this actual area is, but you're definitely welcome to try to compute it yourself. Okay, so let's go back to the right-hand sums for a second. And I want to think about, with this right-hand sum, what could we do to actually make this a better approximation? And the answer is basically to use more rectangles. So I want to do one more example by hand, and then I'll show you on Desmos some other examples with even more rectangles. But I want to calculate R6. So let me just kind of, write that down. So returning to, and you could totally do this with the midpoint or the left hand, but just for the sake of consistency, I want to kind of stick with one type of sum as we increase the number of rectangles. So returning to right-hand sums, how can we get a better approximation than we did with R3? And the answer is basically to use more rectangles. And we'll see why that gives us a better approximation. So what we're going to do in this case is we're going to do 6 rectangles, because that's kind of a nice, convenient way to break these intervals up. So let me just shade in again the actual region we're looking for. So we're going to basically break each of these intervals in half. And so we're going to now have 1/2, 3/2, 5/2. And so now the first rectangle we're going to make is going to be a rectangle where it goes from, where the base is from 0 to 1/2. And so I want to go to the right-hand side of that interval, and that will determine the height. And so here is my first rectangle. And then the second interval goes from 1/2 to 1. And so we're using the right-hand side of that to determine the height. So we go to 1 and use that to determine the height. And so that's our second rectangle. And then our next interval is from 1 to 3/2. So we go to the right side. So that's 3/2, and we go straight up to figure out what that height is. And that's our third rectangle. And then we go to 2 and use that for the height for the fourth rectangle. And then we go from 2 to 5/2, and we use 5/2 to find the height of the next rectangle. So that's 5 rectangles now. And then the sixth one, we use 3 to determine the height, because that's the right side of that interval. So just to kind of compare this, let's look back at the first one we did. So the first one we did, it's very clunky, right? It's like really kind of not actually following the shape of the curve very well. If we look down at this one with 6 rectangles, already we can see that it's a little bit more detailed. It gives us a little bit of a better idea of what the shape of that green region is. So this one, like we said, is R6. So that is a right-hand sum with 6 rectangles. So in this case, we can say, okay, the area is going to be approximately equal to, and so in this case, we have 1/2 is the length, is the base for each of these rectangles, right? So we have 1/2 times, and then how do we find the height? Well, we're going to plug 1/2 into f of x. So f of 1/2. I'm actually going to just write it out like this to start. And then we have 1/2 times f of 1, because that's the right endpoint of the second interval. And then we have 1/2 times f of 3/2, because that's the right endpoint of the third interval. And I accidentally put a times here when this should have been a plus. And then we have 1/2 times f of 2, because that's the right endpoint of the third interval, or fourth interval. And then we have 1/2 times f of 5/2. And then we have 1/2 times f of 3. So in a second, I'll actually tell you what those numbers come out to be for the height. But one thing I want to point out here, and this is going to be a really helpful observation in general for doing these types of problems, is that you can factor out this 1/2, right? So for each of these, this is base times height, base times height, base times height, base times height. And you can think of it that way. That's fine. That's really where it comes from. But a nicer way to write that would be to factor out the 1/2. And then all you have to do is add up all the different heights. And so it's, it's not like a separate formula to memorize or anything. It's just kind of using the distributive property. It's a fact that you can factor out because anytime you're doing this type of problem, you're always going to have the same base for all of the rectangles. And so you might as well just take that number for the base and just factor it out. That will be kind of a useful trick for actually finding, doing this computation more quickly. Okay, so what do you get when you actually plug those numbers in? So you get 1/2 times, so f of 1/2 is 1/4. F of 1 is 1, which I'll write as 4/4. F of 3/2 is 9/4. F of 2 is 4, which is 16/4. So again, we're just plugging them into the function x squared. F of, where are we? Now we're on F of 5/2, which is 25/4. Oops, and then we have one more, which is 3, so that's 9, which is 36/4. And so if you add all of these up, you get 1/2 times 91/4, which is equal to approximately, or no, not approximately, it is equal to 11.375. And so from this, we can conclude that the green area is approximately equal to 11.375. And notice that that's smaller than what we got when we used 3 rectangles. And so that kind of tells us, that makes sense, right? We could tell that the first estimate we did was an overestimate, and this one's still an overestimate, but it's a little bit closer. So how could you get an even better approximation? Well, you could use even more rectangles. And I want to kind of give you a visual to see that. So Desmos has this really cool tool, and I will link this on Canvas. So basically, you can write in a function, and then here you choose what your left and right endpoint are. So here we have the left endpoint is 0, the right endpoint is 3, because we're finding the area from 0 to 3. Then down here, there's this is the only thing I think is a little counterintuitive. You basically just have to read this. So if you want to do a left-hand sum, you slide this thing to being c is equal to 0. If you want to do a right-hand sum, you slide it to c is equal to 1. If you want to do a midpoint sum, you slide it to 0.5. And then this here tells you how many intervals. So right now we're on 3. So I guess I didn't write this down before, but it looks like if we had used midpoints, when I didn't actually find the area is actually 8.75. So this is kind of a nice tool that actually tells you what the area is. You do still need to know how to do these by hand, but if you ever want to check your work, this is a good way to do that. Okay, so let's see what happens. So we started with 3, and let me bring this back to being right-hand sums. So this tells us that the area with 3 rectangles was 14, and that makes sense, right? That's what we found. And then if we slide this up to being 6 rectangles, it says the area is 11.375, and that's what we found earlier too. So let's see what this looks like if we increase the number of rectangles. So let's say we increase it to 12, just give us another kind of nice number. Sorry, it's a little hard to get it to slide exactly where I want it. No. Okay, there we go. So if you do 12, the area is 10.15625. And just notice, now I'm just going to kind of quickly slide this. So I'm going to slide it back to where we were at 3. And we can see how clunky that looks. And then as I slide this to the right, notice how the more and more rectangles you do, it starts to really, really closely match that curve. Up all the way, I can bring this to actually be 100 rectangles. And so that you would never want to draw that by hand, but if you used 100 rectangles, the area, it says, would be 9.13545. So we'll see that when we learn some kind of new tools next week, we'll see that this area is actually equal to 9. So if you use 100 rectangles, you get a really good approximation. It's not exact. The exact area is actually 9. But let me write down a couple of these things. So let's go back. So when we did R12, actually, I already wrote this on my paper. So I I just want to kind of summarize so we can really take a look at the trend. So we saw that R3 was equal to 14. Then we saw that R6 was equal to 11.375. Then we saw that using, not by hand, but on that calculator, we saw that R12 was equal to, 10 point, I guess on my paper, I just wrote 10.16, which I think is, I rounded a little bit, but that's okay. And then we saw on this calculator that if you do 100 rectangles, the area is 9.1, I'll just round it to 9.14. And so basically what's happening is these numbers are approaching 9. So the actual area, so when I say the actual area, I mean the curved area of the green region is 9. And we'll see how to find this more precisely next week. But for now, what I want you to understand is basically, first of all, how to find these areas so that you're just kind of adding up areas of rectangles. And then the really big idea I want you to understand is just that as you increase the number of rectangles, your area gets to be a better approximation, just because of how it can kind of more closely follow the curve of your actual graph. So I want to kind of summarize that, and this is an idea that we'll be coming back to a lot in the rest of this week. But basically what's going on is that, so when approximating an area using rectangles, as the number of rectangles increases, the approximation gets better and better. And so if you want to find the actual area, and again, this is an idea that we'll come back to next week, you actually need to take a limit. So what kind of a limit? What are we doing in terms of limits? Well, what we're trying to do is we're trying to make the number of rectangles get bigger and bigger and bigger. And so what we're really doing is we're saying that the actual area is the limit as n approaches infinity of Rn. So meaning if you keep taking all those different areas with the different numbers of rectangles, if you bring that number of rectangles bigger and bigger and bigger and see what that kind of approaches, that will tell you the actual area. And it doesn't matter if you use right hand or left hand sums or midpoint sums. So even though you'll get different values for the right hand versus the left hand sum, the limit will be the same. And then same thing with the midpoint sums. Because basically the more rectangles you have, the less of a difference you'll notice between the different types of sums. So just to kind of show you that real quick. So let me bring this to something a little more visible. Let's say we have I'll say 12 rectangles. So right now this is a right-hand sum. But if I bring this to being a left-hand sum, it looks also good, right? Now it's below the graph, but it's not so different from this. Whereas when we did just 3 rectangles, they looked vastly different. So as we increase the number of rectangles, basically all of the different types of sums that you do kind of balance out and become really close to what the actual area is. Okay, so there's one more thing I want to talk about today, and this video I think is going to be a little on the longer side, so this would be probably a good stopping point if you're like, okay, that's enough to digest. I would recommend that you stop the video here and then try to do, I think it's the first 2 questions on the worksheet. I was thinking about making a separate video for this next topic, but I think that video would just be really short. So I figured I might as well just lump them in together and, just kind of give you a heads up that you're totally welcome to pause and return to the second half when you're ready. So this next part that we're going to talk about is basically just an application of this idea of approximating areas. So an application, and this application is finding the distance traveled. Okay, so I'm going to start with an example that at first is going to seem like it has absolutely nothing to do with anything else that we talked about, but we'll see in a little bit how it's connected. So let's say that you are driving somewhere, and let's say that you are driving at a constant speed. So you're like maybe on the highway and you have your cruise control on and you're driving at a constant speed of 50 miles per hour. And so the question I want to ask is, how far would you travel between 1 and 5 p.m.? So basically, if you know your rate of travel, you just need to multiply that by the time, right? So if you do, from 1 p.m. to 5 p.m., that would be a time of 4 hours. And so you would just say 50 miles per hour times 4 hours is equal to 200 miles. So that would be your answer. So this is a question that you can answer, without using any calculus, without really using any algebra or anything fancy. But it is actually connected to the stuff we've been talking about in this video. So how is it connected? Well, imagine that you graphed not your position graph, but your velocity graph, or your velocity function. So if you were to graph the velocity function for this trip, it would be a horizontal line at a height of 50. Right? Because again, we're not talking about the position. We're not talking about a graph that shows how far you've traveled. We're just talking about literally a graph of the velocity function. So in this case, your velocity is constant, right? You're always traveling at 50. And so your velocity graph would look like this. It would just be a horizontal line at 50. And so if you're trying to figure out the distance that you traveled between 1 and 5 p.m., so let's say that we looked at this region here. So let's say that maybe 0 counts as noon. And so we have 1 p.m., 5 p.m. And let's look at this rectangle we get here. So notice that the base of this rectangle is 4, and the height of this rectangle is 50. And so basically what I'm getting at here is that the distance traveled is equal to the area of the region bounded by the velocity function between, and the x-axis, I guess I should say. Or let's maybe call it the t-axis since we're talking about time, from t is equal to 1 to t is equal to 5. So basically, because velocity times time is equal to distance, it just kind of works out that if you look at the horizontal distance, that gives you the time, right? And then the vertical distance here gives you the velocity. And if you multiply those two things together, you get distance. And so this is a general fact that we'll see in this class, and it will come up more in detail later. But basically, if we look at the area bounded by a velocity function, the area bounded by the velocity function gives you the distance traveled. There's a few kind of details that I'm brushing over right now, but for now we'll just say that the area bounded by the velocity function is equal to the distance traveled. And that's true even when your velocity function isn't constant. So again, later we'll learn about finding exact areas. For now, we're just still doing approximation. So I'm going to pull up a different velocity graph. So let's say that now you are, oops, and this is, I forgot that this is not attached, so I need to select the whole thing. So let's say that now you are going on, again, some kind of a road trip, but let's say that this time your velocity is varying over time. So your velocity varies over time, as shown in the graph below. So this is a graph, again, of the velocity, not of the position. So you don't, it's very tempting to look at this and think that you're saying like, oh, I'm driving forward, I'm driving backward. This is a graph of the velocity. So the question we want to answer here is we want to figure out how to approximate the distance traveled. And this time, let's do it not from, above we did just from 1 to 5. Let's say we're doing it now over the entire time. So from 0 to 6. Okay, so how can we do this kind of using the tools that we discussed earlier in this video? We can use rectangles, right? Because as we just said, if we were to find the exact area under this graph, that would give us the exact distance traveled, but we don't know how to find exact areas yet. So what we can do instead is we can approximate. So what we're going to do is we're going to use rectangles to kind of fill in this graph. And you can use either right or left endpoints. It doesn't matter. Let me actually, I'm going to copy this so I can show you in a second what left endpoints would look like. Because in this case, the left endpoints would look a little different. Okay, so if we're using right endpoints, basically what we're going to do, let's use 6 rectangles. That's kind of I think the most natural choice here. And we're going to use those 6 rectangles with right endpoints. So for the rectangle from 0 to 1, we're going to go to the height that we get at 1 hour and use that as a rectangle. And then for the second one, we'll go to the right endpoint, which is 2, and go to that point on the graph to get our rectangle. And then here we go to this interval, we go to the right endpoint, which is all the way down here. So you can see how, this isn't maybe going to give the most accurate estimate because of the kind of jumpiness of the velocity. But now we go to the right endpoint at 4, and that gives us this point. And then if we go to the right endpoint here, that gives us this point. And then we go to the right endpoint here, and that's where we get this. So basically from this, we can find all these different areas. And so we can call this R6, right? Because we have 6 rectangles, right endpoints. And so notice that the width of each interval is just 1. So we can kind of factor out that 1, but it's not really going to matter. Really, all we're going to be doing is adding up the heights. So we have 40 as the first height. We have, let's estimate 45 as the second height. We have 30 as the third height. We have 60 as the fourth height. we have 50 as the fifth height, and then we have 45 as the sixth height. And I forgot to add these up on my calculator ahead of time, so I'm just going to do that right now. So sorry for the momentary delay. So we have 40 plus 45 plus 30 plus 60 plus 50 plus 45. So that gives us 270. And so that tells us that the distance traveled is approximately 270 miles. So just to give you another way to kind of think about what we're doing here. So why does this work? Well, basically what we're doing is we're kind of like imagining that the car was driving a constant speed over each interval, right? So if we look at this first rectangle, it has a height of 40 and a width of 1. So we're basically kind of brushing the details under the rug and instead assuming that the car was driving a speed of 40 for that entire interval. And then for the next one, we're assuming that the car was driving a speed of 45 for that entire 1 hour. And then for the next part, we're assuming the car was driving a speed of 30 for the entire 1 hour. So by breaking this up into rectangles, we're kind of ignoring some of the details and sort of breaking, like we're taking this kind of more complicated velocity and trying to turn it into something more like this, right? We're trying to kind of break it into segments, and glossing over the details, we're imagining that the car was driving a constant speed during each of those intervals. So if we try to use left endpoints instead, I'm not going to actually calculate the area, but I just want to kind of point out the difference. So let's say we were using left endpoints, then our rectangles would look like this, right? So we would go to the leftmost part on each interval. And so that would look like this and like this. And here's the left point here. And the left point here is down here. Then we have this point. And then left endpoint here is like this. Okay, so what is different about this? Well, going back to what I was just talking about, we're still kind of doing this assumption where we're like imagining that the car was driving a constant speed during each of these time periods, but now we're using a different reference point for what that constant speed is. So on this first picture, we're imagining that during the entire first hour, the car was driving the same speed that it was at 1 hour, right? At 1 hour, the car was driving exactly 40 miles per hour, and we're extending that to assume it was driving that speed for the whole first hour. Whereas with the left endpoints, we're taking that measurement that happened at the start. So the starting speed was 30, and we're imagining that the car was driving that speed for the entire first hour. And then same thing for the second one. So at hour 2, the car was driving 45. And so for this first picture, we're extending that 45 miles per hour to this entire time period from 1 to 2 hours. Whereas in the second picture, we're using the speedometer reading at 1 hour. So at 1 hour, the car was driving 40, and we're extending that for that whole hour period. So that's how you can kind of understand the difference kind of conceptually between these two. So just to write this down, this one would be L6. And then you could also try midpoints, although I think for this graph, the way I drew it, it's a little bit harder probably to estimate what the values are for the midpoints. All right, so that is it for today. So please do look at the worksheet. Like I said, the first half of the worksheet is just using rectangles to approximate area, and then the second half is some stuff more like what we did in the end of this video. And one of the examples on the worksheet doesn't actually give you a graph. It just gives you a table of different velocities. So what you can do is you can actually draw a picture kind of like what we did here. Or, I think maybe draw the picture and kind of use that to figure out what's going on, but then think about how you could have maybe even answered without drawing the picture. Because really just in the table, you have as much information as you need. Yeah, I'll leave it to you to kind of look at that and see what I mean by that. All right, I will see you all in the next video.